Okay, this much, that CMC curve is cumulative match characteristics curve. What we for drawing it, what we need to do, we need to first calculate this. Excuse me for a moment. Hello.
Yes, sir.
Yeah. Okay. So first we need to form this rank matrix. If you have n persons in your database, then this matrix will be of size n. This matrix, this rank matrix will be of size n. From that, you need to calculate which rank is occurring with how much probability. Which rank is occurring with how much probability. After you calculate the probability, which you of course calculate from frequency, you can plot frequency, then probability, or you can directly plot probability. After that, you need to consolidate the probabilities from left to right, which we call cumulative. Cumulative probability at rank n is probabilities of ranks summing up from 1 up to that rank. That means cumulative probability at rank 4 is probability at rank 1 plus 2 plus 3. That means cumulative probability up to rank 3 plus this one. Okay. So that's how we draw CMC curve. And after CMC curve is drawn, we can somehow understand that, okay, a good ROC is related to a good CMC, and a good CMC is related to good ROC. That is what we feel generally, isn't it? If a biometric system is good, yeah, we can feel that, yeah, its ROC will be better and CMC will also be better. That's what a usual view is. But you realize that ROC curve is a measure in verification system, and CMC is a measure in identification system. And there can be typical cases. Usually both I mean, good ROC implies good CMC, good CMC implies good ROC. In most of the cases you will feel that, but people have shown with some experiments that with for some special kind of score distributions, you can have such score distribution where ROC is good, CMC is bad. Okay, so ROC and CMC are not very much uh, related to each other, that one implies other. How this happens is because you can even get good accuracy, you can even get good accuracy in verification. That means uh, your value is above a threshold, but when you are matching with others, the value, all those values might be above the threshold and more than your value also. So that is how the CMC and ROC are different, and one being good doesn't imply other being good. Okay, there are some articles they have published which this part only, that verification and identification have their CMC. We have told that their own. This is not tell us how exactly this happens, but you can realize this in drawing ROC curve, one was data with himself only, and he was seeing whether that is above a threshold or not, that much. But here in case of CMC, it's a comparison between live query of a data with stored template of the data or other data. Okay, so this is what people published, and I mean there are such examples. Now this I don't think in this semester we can cover it, but there's a concept called Doddington's Zoo. This Doddington's Zoo concept is a concept of biometric managerie. People have developed people have developed a system that looks at biometric system like a zoo, where many types of what happens in a zoo, many types of animals are there, isn't it? Now, due to our own traits, uh, the users can be classified in many kinds. Some users are inbuilt, their features are such that all matches with them. Some uh, subjects features are such that even their own feature doesn't match again. Some features are such that they can be copied or replicated easily. So in this way, there are different type of users, and your performance of the biometric system that you are finding, you are telling at the end of the day, okay, this is 95% accurate biometric system. That 95% is not only the property of the biometric system, it is also dependent on the input, and input is input matrix, and input matrix is dependent on intrinsic characteristics or behaviors of the subjects, how the subjects are actually. If you change the subjects, this code will change. If this code matrix is changing, the same biometric system with the same code is going to give you different accuracy. So the accuracy you are getting from a biometric system, that is not only the property of the biometric system, but also related to the property of the users on which you are experimenting. Okay, so connecting it very clearly, there is a concept of Doddington Zoo. We wish to cover it at the end of the kind of syllabus, but this semester we can't cover it. Later, if anyone is interested, I will give documents on it. You can read through this particular paper also. These are all available. You can understand about biometric managerie. For now, we will keep biometric managerie outside our syllabus. We cannot have it inside our syllabus for this time at least. So you can only the motive behind telling you all this is that you should realize that ROC curve and CNC curve are not equivalent. The one being good does not mean the other is good. Now coming to some other parameters, one is called penetration coefficient. What is penetration? Penetration means how much deeper you need to go in a particular database. Now, if you have these many subjects, with IDs given from 1011 to 1096, and if you are as you are running a identification system, what happens in identification? Which one is best? For knowing that, you have to match your live query with all of them, isn't it? That means you need to know the 100% of the database. You need to check with all the data in the database, and then only you can say, okay, my data matches with 1014 or my data matches with 1015, whatever. But you need to run exactly that many number of comparisons, which is equivalent to the number of subjects in the database. Here in this case, you would run 96 minus 11 plus one number of comparisons, then only you can tell which one is best. That means you are penetrating the total database. You are checking with 100% of the database. What is the time taken for this? Time taken for this, as you remember, is matching for this, and you are actually doing 86 number of matching. I think 86, 96 minus 11 plus 1, I think 80, 86 number of matches you are doing, and then you are telling which one is highest. So if 1:1 matching is consuming 2 milliseconds, you are doing 86 number of matching, it is very difficult to reduce the 1:1 matching time, because that is dependent on your code, and that is the soul of the problem. So a soul of the program. You cannot reduce the 1:1 matching time, but you can always reduce how many times this 1:1 matching will run. Now it is running from here to here. That means 86 times. Let us assume if we can somehow match between these 5 values and can tell which one is best among all of these, then with a less time I can do identification. If I can do identification in a less time, that can be achieved only by reducing the number of 1:1 matching, not by reducing the time of a single 1:1 match. We cannot do that. So there are two parts. Total time of identification is number of 1:1 match multiplied by time taken by one 1:1 match. A single instance of 1:1 match. One cannot be reduced, other can be reduced. So now our target is to reduce this number of matches. We somehow want out of these 86 persons, we would very intelligently match with only 40 or only 20 and then tell which one is better. We do not want to match with all of them. Is it clear that we do not want to match with all the persons, but we want somehow without matching, we want to know which one is best among all. Is it clear? Is the objective clear?
Yes, sir.
Okay. So for doing that, see, we are trying that at the time of identification, we want less time. Okay. And we do not want to search through all the whole database. The whole database is not linearly ordered. If we do not want to do that, like it is from the simple knowledge of data structure, can you tell if I do the whole data linearly, how I can design it somehow? Is there any other data structure where where you do not go exactly linearly, but you can travel a part of the data?
Array, hash map.
Yeah, hash map is one, but here it is not used. Array is array. You need to go through whole data if you are not knowing exactly with which you are matching. Okay.
Tries.
Sorry.
Trees.
I couldn't hear you.
Some form of tree.
Tree, right? Exactly. That is what we will use actually. Usually, what will happen in case of biometric? Somehow, by some characteristic, you are when enrolling the person, you are creating a tree. Previously, enrollment was easy, simple, less time consuming, but this identification was costly, time consuming. We want identification to be faster. We need to compromise on the time of enrollment, but that is fine because enrollment is going to happen once, or very less it will happen again. Re-enrollment or template replacement, that's going to happen very less frequently. So that's fine. If we can somehow compromise and compromise in time and make a kind of different enrollment process, we can have a tree-like structure in the database. As a result, what will happen when we are actually checking for the person, if we have some data about the person, we would just we can easily search one part of the database and can identify him or her. For example, here, if I have 1,000 subjects, what I am showing, I will, while enrolling, I will ask whether the person is male or female. Accordingly, the data will be stored either in this subnode or this subnode, and ultimately, what will happen if this person is male, then I will ask his or her age, and according to her age or his according to his age, the data will be stored either here or here or here. Actually, the here 220 subject means here there are 220, exactly 220 children of this node, which are leaf nodes. They are actually 220 data. Or you can say this is a pointer. After coming to here, you will have a linear list of 220. After coming here, you are bound to go through all 220 data, because they are either linearly organized or all are children of the same parent. If I, after coming here, if the person says that my age is between 30 and 50, I will store his data here. Like for example, there might be 260 data here, 120 data here. So if I have this kind of structure, then what had been the worst case, what had been the previous case of identification? I was looking for the person within a pool of 1,000 people. So I was doing 1,000 number of 1:1 matching. Now if I somehow have information, okay, that the person is male and the person has age between 30 to 50, I will only search 260 subjects. That's all. I will search only 260 subjects. Sorry. And if I know only that the person is male, I will search only 600 subjects rather than searching 1,000 subjects. So if I have some information about the subject, like whether he is male or female or whatever is his age, I can reduce down the searching complexity, searching time. So penetration rate or penetration coefficient is the percentage of, or the fraction of the total database that you are actually searching. For example, if you are searching for a person, you know that he is a male, aged between 30 to 50, that means then you will search only these 260 subjects. So out of 1,000, you are searching to 60 subjects. That means your penetration rate is 26%. A less penetration coefficient is good. A high penetration coefficient is bad. When your penetration coefficient goes close to 100%, that means bad. If you are able to find the proper person with less penetration, that is good. So this is 26%. Now if I remove this information that aged between 50, you do not have that information, you only know that the person is male, then you are searching 600 persons out of 1,000 persons. Your penetration coefficient is 60%. So what is the average? What is the average penetration? If there are equal queries for all these subgroups, like every time you will get a query where you know the age and you know the gender, and almost we are expecting that your number of queries for all of these subgroups will be almost same, then what is the average penetration coefficient? The average penetration coefficient is 1/6 multiplied by 220 by 1,000, 260 by 1,000, 120 by 1,000, 140 by 1,000, 170 by 1,000, 190 by 1,000. So on an average, if you always get queries where you know age and gender, you can expect that you are only penetrating 16.67% of the whole database for on a long run. So that is good. Could you get it?
Yes, sir.
Okay. So
Excuse me, sir.
No, sir.
When you
yeah, please, any one of you can just ask question, please.
so you were saying that if we know somehow that the subject is male or female, so
Right.
how is that somehow that person is directly entering that I am male, or there is
Yeah.
some classifier that this feature belongs to male and female, that kind of?
Right. See, if you want computer to perform any algorithm running for age or for the gender, the problem will happen that will consume time. At the same time, if that decision is wrong, your every decision will be wrong, isn't it? If that decision is wrong, you are going to some other node where the person is not there. whatever algorithm you are going to mess with it, isn't it? So what I meant to say here by telling age and gender, that the
Hello. So you are not audible, I guess.
am I connected? Can you hear me?
Yes, sir.
Yes, sir.
Okay. I just thought that I am disconnected. Yeah. So what I am telling is that here age and gender are taken as two parameters which by which you can actually understand that this kind of tree formation is possible. In case of biometric system, how it actually generate the feature, and it will check whether the feature is more than whether the feature has more number of zeros or more number of ones, maybe, and it will send it to left side or right side in the first round. If it has more zeros than one, it is going to be in this node. If it has more number of ones than more number of zeros, it is going to be in this node. Then if it has more number of zeros, next question is the more number of zero, if the number of zero is double the number of one, it is going to be here. If the number of zero is not double, less than double than the number of one, it is going to be here. This kind of tree is formed. So person is not going to answer about age and gender. What will happen? He will just give his feature. Rather than checking his feature with all, what will be done? Some mathematical formulation will be applied on the feature, and it will be understood in which subnode it is actually belonging. So these categories, male, female, age, these are only to make you understand that somehow there can be some classifier. Age and gender is human understandable classifier. That's why I have used it here for making you understand. In case of machines doing it, they will use whatever is easier for them to understand. They will check whether okay, number of zero is more or number of one is more, or they will zero and number one, make a XOR between them and see whether the answer of the XOR is even or odd. That kind of thing it will check, and it will send it to one of the nodes. Is it clear?
Yeah, okay.
So the person is not going to tell anything. He is just going to give his feature. Also, going to different nodes of trees can happen by hashing. Someone told, that is right. Can also, just by after the person gives this feature, hashing can take place in order of one time, no time actually. So larger, even if they have, the feature is large, it will, the hash time is not going to increase with it. Order of one time, you can find the hash value, and dependent on the hash value, you can move move through a path in the tree. That can also be there. Okay. Someone else was asking another question.
No, so my doubt was also similar. Like I had a doubt,
Okay.
like as we are not giving any other data for identification other than the live query, so how we were going to perform the search? I got it, sir.
Yeah. Yeah. Okay. So this age and gender are just to make you understand. I was going to tell it after one or two slides, but I hope it is clear for now. So if the question that 70% of the queries are males and 30% of the queries are female, then what is the average penetration? So of course, here whatever is here, you multiply those fractions by 70 by 100. Whatever is in the right side, you multiply those fractions by with 30 by 100, isn't it? So you see, if they are equally, the penetration coefficient is dependent on the queries, the rate of queries in different subsets, isn't it? Can you realize that? From this question to this question, the only change is that previously 50% query was here, 50% query was here. Now the rate has changed to 70% and 30%. That 50:50 ratio is now changed to 70:30. As a result, we are finding a change in penetration coefficient. Can you realize that? Is it clear?
Yes, sir.
So the value was 16%, and now it has gone up to 54%. What change has happened from here to here? Only this number of queries is disbalanced. So when you are designing this kind of system, one clever way is you will design it in such a way that mostly you can expect the queries in future to be equally distributed, to be almost equally distributed in different subtrees. If your there are two things that you try to control. One, all these end nodes are equally heavy. Here one is heavier, like this one is heaviest, 220. This one is lightest, 260. This one is lightest, 90. If somehow all of these could have been on an average 1000/6, then no problem. Whatever be this ratio, 70:30, you are achieving best penetration. Second is, if you cannot do it, your first target is to make all these values almost to be same, somehow using some kind of division entry such that all these are same, almost same. If you cannot do that, what is the next way? You try to have you try to have the query, you check the future queries which can come, their rates. If you see that this is 70%, this is 30%, your target is where there is 70% query, make those nodes lighter, first. How you will make those nodes lighter? This kind of tree structure, you need to decide on how you will decide this tree structure. Okay, is it clear?
Yes, sir.
This penetration rate will be reduced only when all these are equally lighter and when there is almost equal number of query for each subnode. That's it. So I mean, you have already understood it, that equally partitioned database is expected to yield a lower penetration coefficient, and lower the penetration coefficient, it is better. You will say that, yeah, I have designed my database indexing in a better way, and that is why I am getting a lower penetration coefficient. That's it. So there is another parameter which is called bin miss rate, and another parameter which we call trade-off between performance and speed, which we call as tau. We are not going to discuss about this. We will somehow see later that these are also important, bin miss rate and tau, but we are not going to discuss about this right now. So moving forward, coming to concluding this chapter, see, the performance measures are designed by some biometric committees, and their reports, how exactly one should code, how exactly the evaluation and performance should go, that is mentioned in a standard, open documents. ISO standard, you all know about ISO standard. In every product you can see ISI mark, ISO standard. This ISO is a standardization organization. So here recording of processes are done. So for biometric, these are the ISO standards that are there. Why ISO standard is needed? Because I will code with my own way. I will say that my biometric system is 80% good. You will code in your way. You will say that your system is 85% good, testing on the same database. But Still then, if our guideline of coding is not proper, your accuracy and my accuracy may not match, may not be comparable. So to compare to biometric systems, one thing necessary is same database. Both parties who are competing, both research groups who are competing, they should test on same database. Second is both should code or evaluate the biometric system. Whatever we have learned, those are the evaluation mechanisms, but there are finer details one should follow, and if they follow, then only their results are comparable. So those finer details are there in these standards. So I mean, if one wants, one can go and see into detail how this performance evaluation is done. So that's it. Okay, no, we are not going to have this question now. So that's all for today. Is there any question? Is there any question?
So actually, I wanted to request you to upload the PPTs you have taught us till today.
See, you have the recorded video. If anyone has done that, you have to follow with that. I mean, I cannot upload the PPTs. They are copyright protected. Some of the usage of these PPTs are prohibited. So I mean, while I am teaching, if someone takes screenshot, I don't have control on that. If someone takes video, fine, but I cannot myself share it. Okay. So I have told it on the first day also. So if anyone wants, one need to take screenshot or record, but I cannot share the PPTs. Okay.
Okay.
Actually, the biometric, for biometric, I mean, it's not like that kind of standardized science. It's research is still going on. Those researchers are still living human beings, and some of them are their inventions, some of them are their designed images, their designed explanations. So for using that, if I want to take permission, I cannot take class. I need to go. I mean, it would take long time. So I mean, I can, for my class purpose, I can show it, but I have talked to many people. They are really against sharing. I mean, I will share with you. You will upload it in SlideShare or somewhere. It will only show my name. So that cannot be done. Okay.
Okay, sir.
Okay. Thank you. That's all for today.